So we have a shorter day 2 for vectors, but still a lot of concepts that you could see on the AP test. So we'll just get right to it. So displacement, which we talked about in the beginning of the year, is net distance traveled. And since we're talking about particles traveling on parametric curves or working with vectors here, if we have some sort of velocity vector, where you have like component A is we'll just call it V1 and component B is V2. And the net distance traveled would be the integral from A to B, whatever those two times are, of the first component of the vector velocity and the integral of the second component. Because if you think about it, that would give you change in position, right? The integral of velocity is position, and that's giving you the change in position for each component. Total distance traveled, remember in the beginning of the year, we just kind of threw an absolute value around everything and said if there's any sort of negative velocity, we'll force it to be positive. Here, remember this absolute value really just means magnitude if we're talking about vectors. And magnitude is calculated again with these two components. Remember, it's just square root of a squared plus b squared. So component velocity 1 squared plus component 2 velocity 2 squared. Really, this is just our arc length formula for parametrics. Remember, V1 and V2 are in terms of t, so they're little parametric equations. So the integral from a to b of the square root of first component squared plus second component squared, that is the arc length. All right, so we're just going to get into practice problems. A particle moves in the plane with velocity vector, this fun thing. At t equals 0, the particle is at the point 1, 5. Find the position of the particle at time equals 4. So this displacement is really just allowing us to use fundamental theorem of calculus, right? So if I know that the x component started at 1, and then had this displacement between times 0 and 4 of the velocity component for x. So I want the integral of t minus 3 pi cosine pi t dt. Whatever this comes out to will be what the new x component is for the position of the particle, right? And position, we'll just call that like r of t. So I'm trying to come up with this number right here. Now, if I have a calculator, then this is really easy. I want to do it without a calculator to kind of remind you that we do have to remember our integration rules. So it starts off not too bad, right? The integral of t is t squared over 2. Easy. But off to the side here, we need to be thinking about like, all right, there's a minus 3 pi cosine pi t dt. So if u is pi t, du is pi dt. I have pi dt. This negative 3 is along for the ride. And finally, the integral of cosine is sine without a change in sign, like not negative sign. So the antiderivative is negative 3 sine of u. So sine of u is pi t. And we're evaluating from 0 to 4. So we do still have to remember our integration rules and just be careful with all of this. Okay, so what is this? 1 plus 16 over 2 is 8. And then when I put 4 in here, the sine of 4 pi, which is the same as sine of 2 pi, which is the same as sine of 0, is 0. So 8 minus 0. Minus, just double checking here, put in 0, you get 0. Sine of 0 is still 0. So 1 plus 8 is 9. And then I'm going to do the same thing, but with the y component. So the y value is starting at 5. And we have the integral from 0 to 4 of the velocity for that y component is 2t minus pi sine of pi t dt. 5 plus 2t squared over 2 will just be t squared. I'm not going to write this out separately. This is similar to what we had before. If u is pi t, du is pi dt, which we have pi dt. The integral of sine is negative cosine, and we have a negative already, so this should be plus, because minus negative. So plus cosine of u, which is pi t, evaluate from 4 to 0. 5 plus, when you plug in 4, t squared is 16. When you plug in 4 here, cosine of 4 pi, so you're at 0, right, is 1, so plus 1, minus, when you plug in 0, don't just assume this is 0, because remember, t squared is 0, sure, but cosine of 0 is 1, so we have to be careful there. Plus 1 minus 1 will go away. 5 plus 16 is 21. So the position at time 4, particle started at 1,5, and now it's at 921. Find the total distance traveled by the particle from 0 to 4. Now, if I were doing this without a calculator, I would have to figure out when is the velocity negative, and I'd have to force that to be positive. I would probably need a calculator to do that, just because I'm looking at this and I see the t's out in front, so that could get tricky. So we are not going to, we are going to use a calculator. So total distance is just going to equal the integral from 0 to 4 of the absolute value of v of t. And as long as v of t is written in the problem, you can write it like that on the AP test, unless you really do want to write the whole thing out. I am going to show, though, I am going to show what that would be. So square root of t minus 3 pi cosine of pi t, that quantity gets squared, plus 2t minus pi sine pi t, that gets squared. Don't forget a dt on the end. And we're going to put this into our calculator. Now you can type it all out, or you can store in your equations. I think I'm going to store in my equations. I don't know. I kind of like doing that. All right, so the x component of velocity is t minus, having calculator issues, there we go, t minus 3 pi cosine, I'm doing a quick check that I'm in radian mode, which I am. And then y is 2t minus pi sine pi t. Double check that I typed that in right. And then I want the integral from 0 to 4 of the square root of the x component squared plus the y component squared. And it thinks about it because it's a lot to calculate, and we get 33.532. So that's our total distance traveled. A particle moves on a horizontal line, not on a curved path, with velocity v of t. Oops, this says v of t equals 3x squared. That should be t. T squared minus 4t minus 10 for times greater than or equal to 0. Find the displacement of the particle from 0 to 4. Now, this is back to the beginning of the year, right? This is like chapter 1, or before chapter, well, I guess, yeah, chapter 1, but now we know how to integrate. So we're moving along a horizontal line. Moving along a horizontal line. So I don't need parametric equations. I don't need vectors. If I want to find displacement and I have a velocity equation that's not in a vector form, I can still just say it's the integral, the net displacement is the integral from 0 to 4 of 3t squared minus 4t minus 10 dt. And again, we'll do this one by hand. So 3t cubed over 3 will be t cubed minus 4t squared over 2 minus 2t squared minus 10t evaluated from 4 to 0. So plugging in 4, we get 64 minus 2 times 16, so minus 32, minus 40, minus double check, you just plug in 0, and yeah, that whole thing comes to 0. So this is what? 32 minus 40 is negative 8. So the displacement is negative 8. Since we're on a horizontal line, remember that tells us that the particle is left 8 units from where it started at time 4. Find the total distance traveled from the particle. Again, in interest of time, I'm going to do this in the calculator by just putting an absolute value around this. That's different than using the arc length formula. This is not an arc length. I don't have two different components here. So if I were doing this without a calculator, I would have to figure out where is the velocity negative, and then I'd have to split up integrals. Like from this time to this time, take the integral of velocity, and then minus the integral from this time to this time where it's negative, and then plus the integral from this, So we're going to save time by not doing that. Now, how do I do this? I can't be in parametric mode here if I'm going to type it into my equations. It doesn't matter if you're just doing it on your home screen, though. So if you wanted to switch modes back to function, you could. But I don't think it matters, so not if I'm on my home screen. So I'm going to do this, and then absolute value. And this is 3t squared minus 4t minus 10 at. I'm getting 35.889. And I don't see any units here, so whatever that distance is measured in. Determine the path that the particle in problem 1 travels from the point 1, 5 to the point 21. So determine the path. I don't want to graph this by hand because it's complicated. I will graph it on the graphing calculator, but otherwise I want to figure out if we can come up with the position function. So let's come up with the position vector, because remember, it's not necessarily a function. So the position vector, we can do it in two parts. We can figure out the x component. We've kind of already done this, right? X of t is equal to the integral. I'm not going to do a definite integral, but it's just the integral of t minus 3 pi cosine of pi t dt. And we already got, back in problem 1, part A, we already figured out that antiderivative. So I'm not going to go through the work of figuring that out again. I'm just going to write it down. So it was t squared over 2 minus 3 sine of pi t, and there'd be a plus c because this is an indefinite integral. But remember, we know that at t equals 0, the x position was 1. So 1 equals, put in 0 for t there, put in 0 for t here, sine of 0 is 0. So c is 1. So x of t is t squared over 2 minus 3 sine of pi t plus 1. So there's the position function. And then let's do the same thing for the y component. So y of t is the integral of, scroll up so I can see it. I can see it right here, of 2t minus pi sine of pi t. And we found that antiderivative back here in part A. So that came out to t squared plus cosine of pi t, and there'd be a plus c with this indefinite integral. And again, we know that y of 0 is equal to 5. The reason I'm not just saying, oh, so c equals 5 is because remember, this is when t is 0. So yes, 0 squared is 0, but the cosine of 0 is 1. So we have to be careful there. C is actually just 4. So y of t is equal to t squared plus cosine of pi t plus 4. And again, I'm not going to graph by hand because then I'd have to pick values for t. I guess I could pick some nice values for t to figure out some points. But you can graph this in your graphic calculator, and it does look kind of cool, so I want to take a minute to do it. Again, make sure that you're in radian mode, unless you're actually seeing that you're plugging in degrees somewhere. And this one was t squared plus cosine of pi t. Is that right? Yeah, plus 4. I'm just going to zoom 6. And then, so it looks kind of cool there. I'm going to just adjust the window, or I guess I could zoom out, but I'm just going to make the window a little bit taller. So maybe we'll bring it up to like 30 or 20. Okay, so yeah, you can see it's kind of cool. It like loops off, goes wild off to the side there. All right. Okay, last example. An object moving along a curve in the xy plane has position x of t, y of t. Here's dx dt, and here's dy dt. Remember, that's another way to say here's x prime and y prime, and that's another way to say that those are the components of the velocity vector. At time 0, the position was 4, 7. Where is the particle at 2? So we're going to use our calculators here. I'm going to put this right in its vector form. The particle started at 4 at time 0, and then there is this displacement between time 0 and 2 of the x component, which is cosine of t squared. And the y component started at 7, and then there was this displacement from 0 to 2 of the y component, sine of t to the third. And I see that all of the x values are different, so this will be kind of nice because I can just do x. I don't see none of these as an option, so I can just do the x. See which one it matches up to. Hopefully it's one of them. So this is cosine of t squared. Oh, close those parentheses. dt 4.461. Yeah. Look at option B, 0.461. This would be like if you forgot to do the plus 4 part. And I bet, I'm assuming if you forgot to do the plus 7 part. So yeah. And I wouldn't have guessed that without doing the math, because it could have been that this displacement somehow was negative. I guess I could do a quick check and figure out whether that's true or not. But anyway, it's always good to calculate rather than just try to be like, oh, it has to be this one. All right, that's it for today. You're doing the odds on the rest of the vector worksheet for homework tonight.